You might remember that last time we sort of left off on a brand new topic, and I don't always enjoy doing that, right at the end of a lecture, starting to pick up a new topic, but it's kind of the way that these lectures are laid out that we run into that issue. But you may have noticed, if you've been buying computers for a long time, that processor speeds have kind of stabilized in the 1 to 3 gigahertz range. You'll see a few that are a little faster. You can get much faster if you cool your system like crazy. But what people have started to do over the years, there's reasons why we've run into this physical limitation of clock speed that we currently see. And there are various approaches for circumventing this, involving making your processor a lot more clever about how it allocates and manages its resources. And so there's a lot of interesting techniques around that. I would say read the chapter 4 of the book if you're really interested in this, because that goes into a lot of the modern superscalar architectural approaches that are used. And then chapter 5 fills me with joy, because chapter 5 is partially about program performance measurements, and it also is about compiler optimization. So you see more of this topic of how do we get faster with the resources that we presently have. Okay? So even though you see this limit on clock speeds, I've bought computers that are no faster than 3 gigahertz for years now. You still see CPUs getting more and more powerful, so that's cool. But what we've also started to do is throw more processors onto the chip. Okay? And so that's a really common approach. You can see this is just some of them, and I know the list goes on because I put that list together several years ago. And so you've got multiple cores now, and they are talking to memory, and memory is still a lot slower than the processor, and so we still have the solution of caching to solve this problem. But as we started to talk about last time, now we have multiple caches of this shared resource, which is memory. And so if you have this kind of an architecture, what problem do we now have? It's really obvious, right? I've got two processors interacting with this shared memory, but they have isolated caches. And we can run into a situation where one processor may read a value into its cache, another processor writes a value into a cache, and those two things are now out of date with each other. They're inconsistent. Okay? So the example that I have here on the slide is CPU 1 reads data in block 23 and starts using it, and then CPU 2 writes to block 23, and CPU 1 no longer is up to date as far as the value that it should be manipulating. Now, there have been processors that have this kind of failure. There's been all kinds of hardware bugs through the years. I'm sure you're aware of a few of them, but there's even more further back that are even worse. And so there are a few processors that have this particular kind of brain damage as well. There's ways around it, but your computer starts getting slower because you have to do extra work to keep things running properly. So what we'd like to do is have some way of coordinating the operations between caches. And so magic is always a good solution. So we're going to have something that sits between these caches, and it's going to make sure that everybody stays synchronized with one another. Okay? So that CPU 1 reads data into block 23, starts using it. CPU 2 writes to block 23, and somehow this magic box will inform CPU 1 that its cached data is no longer valid and it needs to reload it. Okay? Or some other similar kind of solution. Okay? So this is going to be the idea. And we're going to call it cache coherence, because we'd like the caches to remain in a coherent state, a globally coherent state. And so the cache coherence mechanism is what maintains the state of sanity amongst all these isolated caches of a shared resource. Okay? So we need to define how they behave, and so these are a few examples. These are the typical examples given for cache coherence. I read a location X and then write to X, and no other processors modify X between the read and write. So other reads of X after this write should see the value that processor P wrote. processor P1 writes to a location X, and then subsequently another processor P2 reads X, then P2 must read the value that P1 wrote. And it should not see an out-of-date value. So we need to make sure, and of course you can see that there's timing involved here, so we have to have some way of saying that P1's write occurred before P2's read, and a lot of times when you're reasoning about these kinds of systems, you spend a lot of time saying, okay, what does it mean for something to happen after something else? How can I know that one thing happened after another thing? Okay. Processor P1 writes a value to A to location X, and P2 writes a value B to the same location X. So again, P2's write occurs after P1's write. Then processors should see P1's value and then P2's value. They should not ever see them in the reverse order. That would be really bad. Okay? So these are some examples. You could probably come up with a lot of other behaviors that would be preferable in a coherent cache system. So we're going to have some coherence mechanism, and we're going to continue the same approach that we had before, which is that we have our cache lines. And so our SRAM cache still has cache lines in it. It's got a valid bit, a dirty bit, a tag to keep track of what block this cache line is actually holding. And we'll add additional state values, and we'll add some additional operations that caches can perform to build this coherence mechanism. And that's all we really need to do to make this work. Okay? So that process, if you will, a state machine and the additional information and so forth, is called a cache coherence protocol. And there's a lot of protocols to choose from, but it turns out that most of them are based on this one protocol called MSI. Okay? MSI is an acronym that just represents the states that can be used in this protocol. So we have M for modified, S for shared, and I for invalid. And these are basically the states that a cache line can be in. Okay? So CPUs have caches. Each cache line has some state, either modified, shared, or invalid. And there's some set of rules that everybody follows to manage what state line should be in. Okay? So, like I said, you have modified. Modified means that line has data that's been modified by the corresponding CPU. So remember, each cache has its own processor, and if a cache line is modified, then that means that it's got data from that processor. Then you have shared, which means that the line is unmodified, and it can appear in at least one CPU's cache, so that seems okay. And then you have invalid, which is basically a way of saying don't trust the line's contents anymore because somebody else has done something to invalidate this data. Okay? So those are the three states: modified, shared, and invalid. So you're allowed to have a line in multiple caches, so now multiple processors can see it. You're allowed to do that as long as the state is shared. Okay? If you have a line that is modified, then it should only be in one cache, because otherwise that wouldn't make any sense. You'd get into incoherent behavior. And you don't really count invalid in this state. If it's invalid, then you don't care what its contents are, because it won't be trusted. So let's say that we're reading a block from memory, and so the cache is sitting in between and it's doing its thing. And if the block is in the processor's cache, the processor that does the read has the block in its cache, and is marked either shared or modified, we're good, right? We can just go ahead and serve the value, the requested value, out of that cache line. Now, if it's not in my cache, or it's marked invalid, which we'll just consider to be the same state, then we have an interesting situation that we have to figure out. And this is where the coherence mechanism has to interact with the other caches. It could be that no other cache has the block modified. If that's the case, then we're really good, because then I can go ahead and read. The caching mechanism can do its thing. It can draw the next block of data from memory into the cache. It can mark it shared, and then the processor will have that data cached. Okay? If another cache has a block marked modified, now I'm sad, because remember, I wanted to read it, but that other cache has modified version of it. And so what we can do is tell that other processor's cache, hey, you've got modified data. Can you please evict that line, perform the write back against main memory, invalidate your line, or it could always go to shared if it wanted to. And then the processor that's doing the read, its cache can pull the block into its cache and mark it shared. Okay, and then it can go ahead and the processor can get the data that it needs. So everybody see how this works? So this is reads. You can imagine that if another processor has a block marked modified, a lot of work is involved if you want to do a read, because you have to tell that processor's cache to evict the line so that you can see the data, and so there's a little bit of work going on there. All right? So that's if we're doing a read. If we're doing a write, it's possible that I have the block in my cache and it's already marked modified. Then we're really happy because I just go ahead and perform the write. So this is our write back kind of a mechanism. We're going to accumulate writes in the cache line. If the block is marked shared, well, again, I have to be careful because other processors may also have the line. They may have the same block cached in their caches, and it may, it should be marked shared if that's the case. So it will invalidate everybody else's block and mark its own block as modified, and then it can do the write. If the block isn't in the cache or marked invalid, then basically I have to look around again. If the block is marked shared in other caches, then I have to invalidate them. If the block is marked modified in another cache, then I have to ask it to evict and then invalidate so that I can load it and modify it. Okay? So you can see that there's a lot of work on a write. You have to make sure that you coordinate things. If other people have it shared, they have to invalidate. That's not so expensive, but they'll be sad if they have a cache miss after that. If somebody else has it modified, then they have to perform the write back, and then I can read it and perform my modification. So you can see that these operations have varying costs depending on the steps that you have to go through. All right, any questions? That's MSI. And this is how we're able to have multi-core systems that don't lose their minds when they have different pieces of code touching the same data. Now, there's a bunch of ways that people have tweaked MSI, because you can imagine there's probably, and I hope that you, as you look at this, you're asking yourself, well, why don't, if somebody's got it shared, why can't I just suck the data from another processor's cache? That seems like it would be faster. That's a good idea. Or if somebody has the modified block and I want to perform a write, why not just perform the write against their block? That would also be an interesting idea. So there's a lot of optimizations that have been achieved and implemented through the years. You have MSI. Okay, so now we have another state called exclusive, and this is basically a situation where I have unmodified data, and I'm the only one with the unmodified data. Because again, if you think about the way that many programs behave, most of the time when they're reading data and they're working with it, probably there's not going to be other threads reading that same data because that turns out to be complicated to get correct. And so why not, instead of saying it's shared, say it's exclusive, so that if I then turn around and write to that block, I know I don't have to invalidate other caches. So I can go ahead and go from exclusive straight to modified without invalidating any other caches or telling them heads up or anything like that. So you can see that exclusive tries to optimize this scenario where you go from having a read block, a block that you've only read from, to a block you're writing to, and presuming that nobody else is going to have that block in their cache as well. Okay, so that's the idea behind MSI. Then you have MOSI. And MOSI introduces an owned state. And basically the idea is I am modifying this block and I'm going to be doing it a lot, so I'm going to just hold on to it and let other processors, when they need to interact with that block, they can go ahead and use my copy of it. So you can see that owned is a little bit more of a, the cache is holding the block on behalf of multiple processors, not just its own processor. Okay, so you can see that this is going to help in certain circumstances as well. Yes?
These things that you do in software, so like MSI, just happens in hardware.
So I don't know if you would count microcode as software, but this is all implemented on the processor itself. And I would imagine that Intel, being Intel and AMD being AMD, probably have some microcode that scripts exactly how these circumstances are handled.
So the text like we could do one of these.
Yeah, but the hardware is basically what's driving this. There's no software intervention because we're still talking under 10 clocks for L1, and we're talking under 30 clocks for L2. And these cache coherence protocols operate at the L1 and sometimes L2 levels. So it has to be doing this in hardware, but there may be some clever ways that they represent the state transitions and so forth in the processor. Because these processors are crazy now. It's amazing to me how smart they are. And I remember, this is because I started in 29,000 transistor land. Now that we have billions of transistors, everything is insane to me. So, but anyway, that's yeah. You can think of this to an approximation as just being implemented in hardware. Any other questions? Okay. So we also have, how do you pronounce this? Moezi? Basically, this is the owned and exclusive states both together. And that way, you can leverage the benefits of, all kinds of different program behaviors. And this is what you notice. I've been talking to a lot of you about the caching assignment because, unfortunately, the processor's gotten smart enough that the caching assignment had to get harder. And I don't like that. And I wish it was still as easy as it used to be. But you can see that with these protocols that they're coming up with for cache coherence, they're making programs. They're making programs look better and better. You can write a pretty dumb program, and the hardware will just run it and still be pretty fast, even if you didn't give any careful thought to this kind of stuff. So you're seeing that more and more at the hardware level. Okay, yeah, so we can talk about all this stuff. I'm going to let you read about all this stuff yourself because we have a big topic to get to at the end of the lecture, and I don't want to spend too much time. These are peripheral details. This is more of an enrichment topic, but it's pretty important. And if I could come up with a nice, clean, simple problem that illustrated this really well, you can bet you'd be doing it because it's a fun topic to consider anyway. Okay, MESIF. I want to talk about this. So now you have MESI plus another state. So remember, modified, exclusive, shared, invalid, and now we have forward as well. Okay? And so you have situations where caches can share data with each other. So a cache needs to load a line. Well, what we could do instead of having to talk to main memory, maybe it'd be faster to have a cache bus because they already have to be talking to each other to do their coherence protocols. So why not have data able to be moved between caches on this bus? The only issue being if you have like two processors with the same block in their cache and a third processor wants that data, now you have to have some contention or some way of prioritizing or arbitrating between the two caches that can provide the data. And so Intel introduced a forward state that basically allows you to choose one of the caches to be the source of the line for other caches. Maybe it could be the first one that loads it or something like that. And it'll be in the forward state instead of the shared state. So that when other caches ask for the block, they'll get it from the forwarder, not just all of the shared ones. Okay? And again, this seems like a small optimization, but we're talking about a few clocks here, right? We want these caches to be really fast, so the more specialized you get, you can shave off a clock here or a clock there, and your processor performance becomes better. Okay? So there's a whirlwind tour of cache coherence protocols. Any questions? Any other questions? All right. Let's see. So we know that we have a solution for that box. No longer magic. Right? It's pretty straightforward. It would be fun to write a simulator and actually simulate the cache coherence protocol. But then we have other issues that we can run into. Okay? We know that we can make a correct system now. I'm going to assert, and I'm wave my hands and assert that we can create a correct cache coherence mechanism and keep our caches sane so that our programs aren't crazy and produce wrong result, but we still have to think about performance, because remember, caching is kind of a universal consideration when you're doing systems level programming. You have to make sure that you think about caching if you're going to write a fast program. So let's say that you have a program, and it's a single-threaded program, and you want to change it so that it's a multi-threaded program. And you have a system where threads are run on different processors so that you know this is actually a good idea. We have a program that stores its data in an array. So we have 1,000 floats. 1,000 floats won't take very long on most processors, but please, this is a contrived example. You could probably come up with more compelling examples. But, we have this array of floats, and we do some computation. And we know that individual elements are independent of each other, so we could do those things in parallel if we wanted to. So what we'll do is we'll figure out thread A will take care of some subset, thread B will take care of some other subset. They'll run in parallel on the multiple cores that we have, and we'll do things twice as fast. Seems reasonable. But let's say that we decided in our fit of brilliance to have one thread take care of the odd values, or the odd indexes, and the other thread take care of the even indexes. Okay, this is certainly an odd approach. And so now you have this situation where the program is running these two sets of computations in two different threads, and this is our multi-core processor. What will be happening? Yeah. Why would it be shuttled back and forth between two caches? Yeah, do they know that they're accessing the same block? This is what's really interesting about this example. Right? So I've got my program. Clearly the program is written. I've got 1,000 floats. I can update each one independently of the others. So thread 1's computing X on some, let's say X3. That seems perfectly fine. And then thread 2's computing X on the 4th index. That seems perfectly fine as well. But the problem is, are these things actually independent from each other from a caching standpoint?
I was just also going to say, it seems so inefficient to have them adjacent and having them only working on half the values that they're grabbing at a time.
Yes, so there are other issues here. This is not a great stride. And if we wanted to achieve maximal stride, then that by itself would automatically steer us into a much better solution. I'll just tell you that. That's a very good observation as well. But we do have this issue that the cache coherence mechanism is working at the unit of blocks, right? 64-byte blocks. And we've got floats, which is the unit of computation that the program is working with. And so even though the program thinks that you've got adjacent values that are independent of each other, the cache doesn't know that, and it can't do anything about it anyway because it was hard-coded to work with 64-byte blocks. So problems? Yes, many, right? So this kind of issue is called false sharing, where you have the cache having to maintain coherence in a circumstance where the program is written and it doesn't care. It knows that these values are independent of each other, but they're in the same cache line, and unfortunately that's the best the cache can do. It can't get any more granular than that. Okay? And so you have the cache coherence mechanism saying, oh no, core A updated this part of the cache line. Oh no, now core B wants to update this part of the cache line. So it's having to do its little MSI protocol back and forth and try to deal with this mayhem that's going on. Okay? So, yeah, you have something like this going on. X3 loads a cache line into that processor's cache. So that'll invalidate whatever was going on in other processor caches, and then X4 gets computed, and that invalidates the work that was just done by the CPU1 cache. And you have this going on back and forth. So we call it ping-ponging. There's a great term, I love this term. It's called ping-ponging, where you have the cache line ping-ponging in between the various caches because the various CPUs are operating on the line even though the data they're updating is completely independent of each other's processors. Okay, everybody got it? This is terrible. This is an awful circumstance to occur. There was a research paper that showed that with false sharing and ping-ponging, the program performance slowed down by 100-fold. Yuck. That's terrible. You know, you think, oh, I've got one core and my program is X fast, and then I'm going to run it on 4 cores, and clearly it's going to be 4 times as fast because these are entirely independent computations, and it's like 1/100th of the performance that it used to be. That's terrible. I would hang my head in shame if that was me. So you have to pay attention to this kind of thing. If you have a cache coherence protocol that can do some things about this, like the owned state is kind of your big winner here. Now instead of ping-ponging that line around, you have everybody hitting the one poor cache that happens to be holding the line. Okay, so you can see that an owned state would definitely mitigate this kind of an issue. And that's what I think is really interesting, because it's kind of boneheaded to write a program to do this. You know, when I present this example, I hope you look at that and say, that looks really dumb, Donnie, because if you do, then you'll fill my heart with joy. But the processor is getting good enough to make boneheaded programs run okay. And that makes me really sad, because I feel like there should be a penalty, a visible, clear penalty for writing bad programs. Okay? So hardware is getting good enough that it can make bad programs look pretty decent. I guess the upshot, though, is that good programs will look amazing. So. Any questions? All right. So how do we avoid false sharing? Well, we just make sure that entire cache lines are the units that a thread or a processor is actually working with. That's easy enough. You'd be doing that anyway if you were trying to make a cache-friendly implementation. So if, for example, you said threads update contiguous groups of the X array and make sure that that's some whole multiple of the cache line size, then you'd be really happy. Okay? And of course, you could always pad things out to cache line sizes if you really were worried about this kind of thing. But honestly, if you're just updating an array, then you could like cut it in half or something like that. And if everybody's going linearly through the array, then by the time one thread gets to a block that another thread touched, it's probably already ready to move over without any problems. Okay? So there's various things that you can do to improve this. So multi-core complicates this whole caching issue, this caching topic. You have to think about how cache coherence affects cache performance as well. And obviously this is in one important circumstance. This is where you have multiple cores touching the same data. If multiple cores are touching different chunks of data, you don't have to think about this. And you just think about run-of-the-mill caching, cache performance. But it's when you have multiple cores touching the same chunk of memory that you really start running into cache coherence issues. All right. Any questions about any of that before we start talking about the next aspect of cache coherence? All right. So we also observed that in our example, we had 2 parts of the same program participating in the same computation. But a lot of times when we have multiple cores, we're not actually using them to run the same program. And we might have one program that's very memory intensive and another one that's I/O intensive. And so it doesn't actually need to have very much memory because it's spending most of its time waiting for things to happen. Okay? So you have CPU 1 running a MATLAB program to do some giant computation. And CPU 2 is where you're watching your cat videos. Okay? So you have something like that going on. Okay? CPU 1 is wanting to use as much memory as it can, and so it's leveraging its cache, and CPU 2 is not. And so now you have kind of a sad situation in which this design doesn't allow CPU 1 to take any of CPU 2's cache and use it for its computation. So we'd like to have a way of dynamically shifting resources to the processor that needs it based on the actual behavior of the processor. Okay, so hopefully all of you can see that this design has this limitation that we can't really shift resources if you have one processor doing something memory intensive. So this is why many times you'll have multi-core systems with a shared level 2 cache, because then that allows the cache resource to be shunted to the processor that actually needs it the most, just using the standard eviction algorithms and so forth. Okay? One processor is touching a lot of memory, so clearly those things will appear to be frequently used or recently used, and so less frequently used things will be evicted, and you'll end up with one processor holding, the bulk of the lines if it happens to be doing a lot of memory interactions. Okay, so you have a shared L2 cache for all the cores to use, and then CPUs can proportionally utilize the shared cache based on the needs. So you're looking at cat videos while your other core is doing its MATLAB computation. Well, MATLAB's going to get most of the L2 cache, and it's going to be happy. And remember that cache will be like tens to hundreds of kilobytes, typically. Okay, so the level 1 cache is very small, it's very fast, so we want to have really good locality to leverage that one, and that's going to be typically 32 kilobytes, something like that. And then the L2 cache might be 256 kilobytes, or it may be all the way up to a couple megabytes, depending on the processor. And then that can be shared across multiple processors. It's a little slower, but it's sure a lot faster than main memory, and so that's why it's nice to have it there. Okay? Make sense? That's the idea. L2 cache also is pretty interesting because you start noticing that you can have two programs, two cores, sharing data between each other using L2 as opposed to going all the way out to main memory. Okay? So this is kind of an interesting thing. CPU 1 writes some data to memory, gets cached in L1, and now instead of that having to go all the way out to main memory, it can just move into L2 and then be accessed by CPU 2. So now you're talking, instead of 100 clocks, you may be paying 15 clocks to access the same data that CPU 1 was accessing. Okay? You can also see that this will improve the performance of cache coherence, right? Because a shared cache, if you have two processors that are sharing an L2 cache, then Coherence can use those instead of going all the way out to main memory. So this does mitigate the issues of poorly written multi-threaded programs as well. Okay, any questions on that? Does it make sense? Okay, so yeah, greatly mitigated, blah, blah, blah. I was talking about this. So shared L2 cache, yeah, so false sharing can still greatly improve your performance, but at least it's not going to be as horrendous as if there was no shared L2 cache. Okay, so that's that. So multi-core. Multi-core is really fun. I love multi-core. I wish we could talk about it more in CS24 or in some other class, but we just haven't gotten, there's just too many things to talk about, unfortunately. These systems are so sophisticated. But it does introduce a lot of fun, new, exciting problems to solve in how programs leverage hardware caches, how hardware caches work with each other, and so forth. And so protocols like MSI help us a lot. They do make the logic more sophisticated, more complicated, but they also help our programs stay sane. Okay, so so here's some benefits. Oh yeah, shared L2. So this is talking about the level 2 cache, having a shared cache so that we can actually proportionally allocate memory based on the processor's need. That's always nice. And then we have to think about false sharing as well. Just a summary of what we've been talking about. Okay, any questions about caching? Alrighty, so that's basically all we're going to talk about caching until we get to virtual memory. So you can't forget it after this week. But yeah, this is all we're going to talk about with hardware caching right now. Because we're going to start talking about a new topic, which is really one of the neatest things that you can do with a computer, I think. But we have programs running on our computer, and so far we've only talked about our computer as if it can run one program at a time. Now we all know that's not the case, right? I'm running like probably well, 4 or 5 applications right now on my laptop while I talk at you. We know that QuickTime and PowerPoint are both running, and there's a whole bunch of other things running as well. And all of you using your computers also have multiple programs running at the same time as well. So the question is, how do we actually build this mechanism? Because we know that programs frequently are doing nothing or not fully leveraging the compute hardware. There's only a few kinds of programs that really try to maximally utilize the compute hardware. One of them would be computer games. That's one of the reasons why I like computer games a lot, because they actually try to maximally utilize most of the computing resources the computer has to offer. Okay? There's probably a few other examples that one could come up with, but that's one of the few. What do you think programs mostly do? Yeah, wait. Most of the time programs are bored. They're twiddling their thumbs. Like, what do you think PowerPoint's doing right now? Like, when is he going to press the next key? That's all it's doing right now. So, think about things that programs interact with. You have data being read or written to a disk, and so you have tens of milliseconds of latency being introduced. Maybe if you're interacting with a solid-state drive, you're lucky and you have tens to 100s of microseconds being introduced. Interacting with a network. Networks aren't great, but they're getting faster and faster, so you'll have tens to thousands of milliseconds of latency. And then you have users, and users are the worst, because users have this tendency to wander off and do other more interesting things. So what's the program going to do? Wait, that's all its option really is. If you have multi-core processors, well, now it's even clearer that you have multiple programs that you can run at the same time, because you could give one to each core. But we could probably do even better than that, because most of the time our programs are going to be waiting. So we'd like to have a way of running multiple programs. Okay? What's the number one constraint that our computer should be able to enforce if we have multiple programs running concurrently? You can't steal my bank account information. Your program misbehaving can't bring down my program. How many times have you had a program segfault in this class so far? Probably a lot, right? So that hasn't hopefully brought down other programs that are running at the same. If it has, you should have a talk with your operating system. But we basically would really like it if programs can't meddle with each other in any sort of dastardly way. Okay? They shouldn't be able to access data, unless, of course, both programs agree to it. That certainly could occur. It happens quite frequently in program design that you want multiple programs to collaborate. A crash of a program shouldn't crash other programs or the computer itself. We need a way of isolating these programs from each other. Okay? So how do we load and run programs and have them run concurrently? This is the big question that we need to figure out. Let's say that we want to run Firefox and GCC. It's really great because it used to be that everybody used Firefox. And then Chrome came along and Firefox got beat. And now Firefox is better again. So I feel good again having Firefox. I never changed the slide, but we're going to stick with Firefox. It's the long race that matters. Okay, so programs have their own code and data. Notice Firefox has to have a stack. GCC has to have a stack so that they can make function calls. They both have heaps for obvious reasons. Firefox needs to have data or space to store the cat video, and GCC needs to have space to store your program. And then you have your read-write data, which tends to be your globals. And then you have your code and read-only data. Okay? So the code needs to refer to its state. And the question is, how could we load both of these programs into our computer's physical memory? Clearly it has one giant address space with all of its memory in there, and we need to somehow get these programs into it. Well, here's an idea. We'll just give each program its own address range. That seems like a great idea, right? So Firefox always has to live between these addresses. GCC always has to live between these addresses. hopefully you will look at this and say, Donnie, that's a terrible idea. I hate it. I assert that it has all kinds of problems. What problems can you come up with that this has? Yeah. Yeah. So what happens when Firefox decides it needs more memory? And it needs to allocate. Where is that allocation going to occur? Now our lives suddenly got horribly complicated. What's another issue? There's a really obvious one. Yeah.
You can have a lot of programs and then you end up not having enough space when you actually could have enough space for them.
Yeah, you could run into situations. Well, so for example, you could have multiple programs that ended up like, well, what do? I have a lot of different programs that I might want to run, and you might end up with a program wanting an address range that isn't available. That would be bad. What about having 2 copies of GCC running at the same time? You're not allowed to do that anymore with this approach, right? So you can imagine, yeah. Well, if GCC were statically allocated a particular address range, you're stuck. Because remember that the way that these programs are generated, at least, it's funny because this was true all the way up until IA32, you would have a lot of static address assignments in the program, directly implemented in the program code. Now with things like RIP relative addressing in x86-64, because remember, now that we have a 48-bit address space, addresses are giant. We don't want to store them in our code if we possibly can avoid it. And so we do things like RIP relatives, so it's going to be a lot more space efficient. Okay? So having absolute address ranges that we compile into would be less common going forward. But still, I mean, like, why would you even do this in the first place? Okay? So anyway, issues, right? What we would like, hopefully this horrible example will illustrate a very simple concept, which is that we'd really love to have it so that each program thinks that it is the only program running on the computer. And if you think about it, when you connect to your program running the debugger, that is exactly the abstraction you see. You poke around in your program's data, you look at your program's code, you only see the one program. You don't see any of the other programs running on the computer. You don't even see the debugger. You just see your program. Okay? So we'd love to have this abstraction that the program is the only thing using the computer. We'd like to isolate the address spaces from each other so that we could even have 2 programs with different things at exactly the same address and nobody cares because program 1 has its own view and program 2 has its own view. Okay? This is what we would like to achieve. We'd like the processor to take care of this for us. You know, we're asking for things and we're saying, and I'd like a pony. So the processor will sort all of this out for us, but this is what is necessary if we're going to run multiple programs with large amounts of resources that they need or multiple instances of the same program so that they can have things at the same address. Okay? Notice, we also have the register file. We only have the one register file on each core or on the processor. We'd like programs to not have to think about what other programs are doing with the register file and so forth. Everybody got it? This is the idea. We'd love to be able to create this abstraction. And honestly, this is probably one of the most central concepts in operating system implementation. How do I create an isolation between different running programs? That's like one of the #1 things that an operating system has to provide effectively. That is one of the central themes you see across all operating systems. So we virtualize the processor so that it looks like we have multiple processors. Each program thinks that it has its own processor. Okay? So this is another level of abstraction. So we have the machine that is actually in the hardware, and then we have the machine that the program sees. And those are different. We have some way of virtualizing the processor. Okay? Everybody got it? So this is the idea. Also, we will figure out a way of virtualizing that big yellow box at the bottom. We want to make it look like every program has sole access to memory. Okay? And so we're virtualizing memory as well. So they can do whatever they want. They can manage the heap however they want. One program can have one kind of heap allocator. Another can have another kind of heap allocator. One program can decide to crash, spraying mayhem everywhere, and the other program is like, eh. So all of this we can do with virtualization. Okay? So, and like I was saying, this is one of the most fundamental concepts in operating system implementation. There's a few others as well, but this is ubiquitous. Okay, any questions about this high-level concept? All right, so this whole concept of having a virtual processor plus a program running on it, that is called a process. Okay? So you can imagine that the process is a program plus its execution context. Okay? An instance of a program in execution. So it's the program as well as all state associated with the running program. And that state is called the context. Okay? It would just be like if you love cooking. I don't know if any of you love cooking, but the cooking class at Caltech always seems to be really popular. And you've got your recipe. Your recipe is the program. And then where you are in your recipe and your bowl of eggs and your bowl of dry ingredients and whatever else you need for cooking, that's all the context. Okay? That's the idea. The thing that's a little bit bewildering about this is that the processor, there's still only one of them. There's still only one physical processor. So we are creating this sort of illusion that we have multiple programs running at the same time. Okay? So the idea is if we have a way of capturing the context of a running program, and we can save it somewhere, and we can restore it back onto that physical processor, then we can just time slice access to the processor, so that each program gets a little bit of time on the processor. Okay? And so, like I say on the slide, a program has exclusive access to the hardware while it has the processor, but then it gets suspended and somebody else gets a go. And while somebody else is running, that program has no conception of the passage of time or that it's not on the... Because it's just, its context is saved somewhere. It's like a snapshot of its brain has been saved somewhere. So what state does a program have? This is something that hopefully all of you can say, this is what I think it includes. Right? We got the program itself. That's pretty obvious. What else? Well, we need registers. Yeah, so probably we have register state that we need to save. That's part of its context. State of the heap. Does that seem like a good one to save? State of the stack? Yeah, so hopefully you can see how the context would include these things that we know the program already has running. So we have the register state. And of course you'd also have your floating point and MMX SIMD registers, all of that kind of malarkey all saved somewhere. Okay. We have the program counter, the stack pointer, frame pointer, just in case your program happens to be using the frame pointer. And the flags register. We need to save and restore the flags as well as part of the program's context. Because imagine if you got interrupted, you had the processor, you were just building up to do this big comparison. You did all the calculations, you did your comparison, and then you're booted off the processor. And when you come back, you need to know the flag state so that you can do the right thing. Okay? Of course, we also have memory that these things reference, so we need to save all of that as part of the context as well. Okay? So this is the context of our running program. So we have an idea of what we need to save. We're not going to talk about how to do it yet, because the mechanism that we're going to propose right now is actually really dumb. It's really slow, and nobody in real life should ever do it this way. But what we're going to do is switch the processor from running one process to another by stopping the current process somehow. Because remember, a process is a program in execution. We need to get in there, save all the context, so save the register state, save the memory state, save all the other state we need, load some other process's context back onto the processor, and then go back to where it was. If we can figure out a way to build this, then we can implement this virtual processor abstraction. Now there's two ways that we can switch between processes. One is everybody's nice. Everybody plays well together. It's called cooperative multitasking. So one process, as it's running, will say, you know what? I've had a lot of time. It's been a great run. I'm going to yield the processor to someone else. So it gives up the processor voluntarily. The issue is, if you have a program, let's not say it's malicious. Let's just say that it had an infinite loop in it that you didn't know about. Well, now it's running and it never gets to the point in the program of yielding the processor to someone else. So that brings your entire operating system to a halt. Okay. Windows up until Windows 95 had this problem. And same thing with Mac OS up to a certain point had this problem as well. Because they both used cooperative multitasking. Then you have preemptive multitasking. This is basically where you have a time limit. And when the time limit runs up, I don't care if the process is in the middle of something, it's stopping. Okay? So you interrupt processes forcibly after a certain time so that someone else can get to run. Basically, all Unixes have always implemented preemptive multitasking. And Windows since Win95 and Mac OS since whatever, I can't remember the version, both implement preemptive multitasking as well. Okay? I don't know if any of you ever got to program computers that used cooperative multitasking. It was kind of an interesting experience, but now it's not a very common experience anymore. So we have several programs running at a time. We're going to keep a simple example. Web browser, instant messaging client. Now everybody uses Facebook Messenger. I suppose that's not necessarily a thing anymore. These are all becoming your web browser, right? Email client and text editor. What's the common theme amongst all these programs? They all wait a lot. They wait on different things, interestingly, but they all wait a lot. Okay? So let's say that we have memory somehow, somewhere, that we can store all of these contexts in. Okay? And we have a magic box. In the bottom left, this is the running box. Whatever context is in there gets access to the processor. Okay? So it's running away. It doesn't get to see anything outside the box. Okay? Doesn't have to think about anybody else. It just does its thing. But at some point, it gets suspended. We don't know how yet. And what we need to do is copy its context out of the magic box back into wherever we keep contexts. Okay? So all of that stuff gets saved somewhere. Then we pick somebody else and copy their context into the magic box. And then we can go ahead and resume it running. Okay? Now the new program has no idea that it wasn't running, and it doesn't have any idea that there are other programs running on the computer. Does that make sense, everybody? So this is the idea behind processor virtualization. The last thing that I want to mention is that you can look at this from the standpoint of physical control flow, because you still have one processor. It's just hopping back and forth between these different programs. So the physical control flow is only one thread of execution, if you will. But then you have a logical control flow within each one of these programs. Each one of them looks as if it's got sole access to the processor. Okay? So we call this concurrency, and I want to make sure that everybody understands. Thankfully, it's pretty common knowledge by now. Concurrency is having overlapping logical control flows. Parallelism is doing multiple things at the same time. This picture is not illustrating parallelism, it's illustrating concurrency. So with one processor, I can still have multiple concurrent executions, but if I have multiple processors, then I actually get parallelism, because they can be doing different things at the same time. Okay, any questions? Yes? That is a great question. How do we decide with preemptive multitasking when we should interrupt somebody? We will talk about that a lot in a week or two. Okay, any other questions? All right, so what we're going to do for the next few lectures is develop this idea, and you'll get to experiment with it in the next two assignments as well. So we'll see you next time.